Moving on to differentiation. Okay, we're starting off with the product rule. Just turn that off. Cool. Okay. We are starting off with a product rule. Okay. Which, you know, but a question like this. So, does anyone know how other than knowing, like, what's a product rule, can you differentiate this based upon your AS knowledge? Yeah. You can, yeah. How would you differentiate it based upon AS? Well, you can't do chain rule. No. Chain rule only works when you've got a single bracket with a power. You'd have to expand it, okay? So looking at this equation, you'd have to expand your x plus 1 to power 4, and you'd have to expand your 3x minus 2 to power 3. Okay? Load of work, and then you'd have to multiply those two things together, and then you'd have to differentiate it as a string, basically. Okay? But we're going to learn the product rule, because what we actually have here is two things times together. So we can treat this as y equals uv. Okay? Where the first thing is u, and the second thing is v. Okay? And when you differentiate with respect to x, uv, what you end up with is u dv dx plus v du dx. Okay? And that is the product rule. If you've got two things multiplied together, you can consider it as a first term times the differential of a second term plus the second term times the differential of a first term. Okay? And you just learn that and you do it. That's it. So, if u is x plus 1 to power 4, what is du dx? Which one? There's a v, u and a v. There's a u and there's a v. The second d, yeah, that's a du dx. It's got a stem. What are you on about? U, dv, v, du. Do you know, like, that is clearly a v. Like, yeah, I don't know what's wrong with Radica. Like, do your u's and v's look the same? Mine definitely look different. Yeah. Right, anyway, moving on. Okay, so, how do we differentiate x plus 1 to power 4? Chain rule. Now we use our chain rule, yeah. Okay, so, guys, chain rule, if you've forgotten it, if you've got a function with a power, it becomes n times the derivative of a function times the function to power n minus 1. Okay? Or something like along those lines. So we're going to multiply by the power, which is 4. What's the derivative of x plus 1? 1. So multiply by 1, so we're not going to multiply by anything. So then x plus 1 to power 3. Is that okay? Cool. Alright. We then treat our second variable as v, which is 3x minus 2 squared. And then we do dv dx. What is the derivative of our second part? So again, multiply by the power, which is 2. What's the derivative of 3x minus 2? 3. So 2 times 3. Oh, is it power 3? Oh, sorry. So 3 times 3. 3 times 3. 3x minus 2 to power 2, which just becomes 9. 3x minus 2 squared. Okay. And then, once you've got your dv dx and your du dx, we put it into this form, which is just u dv dx plus v du dx. So, dy by dx is going to be equal to my u term, which is x plus 1 to power 4, times dv dx, which is 9 3x minus 2 squared, plus my v. Again, I'll write these out. That's u, that's dv dx. And then it's v du dx. Okay, which is 3x minus 2 cubed times du dx, which is 4x plus 1 to power 3. Okay, in this case, we can then expand and simplify. But I would rather just write this as one rule. Or one thing. So, first of all, you've got 9x plus 1 to power 4. And then 3x minus 2 squared. Plus 4. I'm going to write them in the same order. So, I'm going to put my x plus 1 bracket first. And then my 3x minus 2 bracket second, like I did with the first one. Because what you can realise now is that there's potential to factorise this out. Okay? In both terms, or both parts, there is a certain number of x plus 1s, and there's a certain number of 3x minus 2s. So we can say that this is equal to x plus 1 cubed, 3x minus 2 squared, times 9 lots of x plus 1 plus 4 lots of 3x minus 2. Okay, which is also x plus 1 cubed, 3x minus 2 squared, times 9x plus 1 plus 4x minus plus 12x, so that's 21x, plus 9 minus 8 plus 1. Okay, although they got 10x plus 11. Oh, hang on, am I looking at a different question? Yeah, plus 1, cool. How did that go to that?
How did 2 go to 3?
That line to that line?
Sorry, yeah.
That one?
Yeah.
Similar terms that you can factorise out?
Yeah.
So I can take out x plus 1 cubed. I can then take out 3x minus 2 squared because there's 3x minus 2 and 3 squared and cubed, leaving me with just an x plus 1 in my first term and leaving me with just a 3x minus 2 in my second term. I also look at the book and the book tells me, but yeah. But then once you're there, you can simplify that that third bracket. Okay. So now it's just one single product. It depends on the question, because technically, this is that there is technically a fine solution. Okay. It really depends on what they want. They might say as one single product, and then you might want to do what I've just done. But in reality, I could have just left it at that second line, because that is the differential of my original thing. So it really depends.
You could have left the second line?
Yeah. Theoretically. Depends on the situation. Depends on what they're asking for. Okay. There is a proof of it. I'm not going to go through the proof from first principles, because I don't know how many of you have done first principles of like differentiation in the first place. Looking at limits of infinity, you know, progressing towards 0 and stuff. Maybe. I don't know. So, let's have a look at the second. Do you want me to do the second one? I feel like this is fairly standard from here. Mainly it's a lot of products. It's just product rule. As long as you know u dv dx plus v du dx, it's real simple. So, if y is equal to 2x minus 1 times root 4x plus 5, this is where this becomes more useful, because in our first one, we could expand out that. We could easily expand out that. Okay? That's doable. We can expand out power 4, power 3. But here, what power do we have? Half. Okay? And yeah, you can expand it when x is less than a certain value. X is very small. In this case, it'll be, what? X is less than a quarter. Or between a quarter and negative a quarter, because of our binomial expansion where n is not a positive integer. You remember that? Where it goes on infinitely. Yeah? We did it like 4 weeks ago. I know that feels like a long time ago, but did it 4 weeks ago. Okay. But we don't want to do that. So we're going to just say this is u, this is v. Du dx is just going to be 2. dv dx is taking the v, which is 4x plus 5 to power half, and changing that to a half times 4x plus 5. Oh, I'm running out of space. Oh, no. Okay, 4x plus 5 to power negative a half, which is just 2 4x plus 5 minus a half. Okay? Everyone okay with that? Cool. So, write it as one single thing. dy by dx is u dv dx. So, 2x minus 1 times r times 2 lots of 4x plus 5 to power negative a half plus v du dx. So, 4x plus 5 to power half times 2. Okay. From there, you can write it as 2x minus 1, 4x plus 5 to a half, negative half, plus 2, 4x plus 5 to a half. Okay. They've decided that at that point they want to write it as a single thing. Not necessarily. You know, you can do it without. But I'm just going to do it for the sake of doing it. So expanding out our 2 times 2x minus 1, because we might as well, because that's easy. 4x minus 2. That is over root 4x plus 5. We good with that?
Yeah.
Okay, because negative half means 1 over, half means root. And this is 2 times root 4x plus 5. Okay. To combine it as a single fraction, we're going to times both the top and bottom over here by root 4x plus 5. And treat this as over 1, which gives us 4x minus 2 over root 4x plus 5 plus 2 lots of 4x plus 5 over root 4x plus 5, which is 8x plus 4x, which is 12x. 2 times 5 is 10, minus 2 is plus 8 over root 4x plus 5. That's how they've simplified it. Again, unless they state otherwise, that, I think, is technically a fine enough solution for most cases. Okay, because a lot of time it's find the gradient at this point, or at maximum and minimum. So it's things that you learnt last year where it's just substitute the values into that equation. Okay, it's very rare that you need to then go down all the way to the bottom and rationalise a denominator, which you've not probably thought about since year 11. Okay, it's just the book likes to go and show the full what you can do with these things. It might say to simplify it as far as possible, and that's when you'd want to do this all the way down to here. Simplified as far as possible. But it really depends. Depends on what we want. Okay? Any questions about that? Really, it's just using that identity that I highlighted at the start. That one there. That's really important. And there's going to be a similar one for divide later on called the quotient rule that we'll look at. But that's about it. Okay? Any questions?